All right. Hi, everybody. I think a few more people will probably trickle in over the next 5 minutes or so, but let's get started. This is our first seminar of the year without Victoria running things, so I'm managing the recording and the administration. Hopefully all runs smoothly. You can direct your ire at me if it doesn't, but it's my pleasure to have virtually Paula Plante, who's a postdoctoral fellow at the BCCP, the Berkeley Center for Cosmological Physics, and someone I've been working with for a number of years now. So thanks for showing up early in your morning and presenting to us, Paul. So please take it away.
Absolutely. Thank you so much for the invitation. I'm delighted to be here today. As Jonathan said, my name is Paula Plante. I'm a postdoc at the Berkeley Center for Cosmological Physics. And today I am delighted to be talking about looking toward cosmic dawn with computer vision. So just to kind of give a quick overview of what I'll be talking about. So I'll start by kind of situating and motivating the science case with what we call cosmic dawn and reionization. Then I'll talk a little bit about artificial neural networks, which is a technique that I use in a lot of my research. And then I'll talk about specific applications, excuse me, of these neural networks. And then finally, a little bit about what I'm working on now and where I'd like to go in the future. So, and I would also like to say at the top here, just feel free to, ask any questions you have as we go along, unmute yourself, wave. I have Zoom open, so hopefully you'll catch my attention, but always happy to answer things as we go along. So feel free. All right, so to begin, just talk a little bit about cosmic dawn and reionization. So start here with what I think by law has to be in every cosmology talk in the opening slide. So this is the history of the universe in a single picture. So on the left here, we have the Big Bang about 13.7 billion years ago. On the right, we have today. You can see we have the cosmic microwave background in here, about 380,000 years. So the portion of the universe's history I'll be talking mostly about is what we call cosmic dawn and the epoch of reionization. So that kind of falls around here on the timeline. So starting around 200 or so million years after the Big Bang, going to about 1 billion years, we have the formation of the very first stars and galaxies. So before this, we have just neutral baryonic matter and dark matter filling the universe. And then eventually, the very first stars ignite. And as they burn away, they shine ultraviolet light, photons, into the low-density gas between galaxies that we call the intergalactic medium, or IGM. And as these photons propagate, they ionize the hydrogen gas that they encounter. So it fundamentally alters the state of the IGM. So we go from mostly neutral to mostly ionized over the course of a few 100 million years. So it's really kind of a very interesting, very fascinating part of the universe's history. But unfortunately, right now, we don't know all that much about it, actually. So we kind of know this broad picture because we observe the universe, it's ionized today, but we don't know exactly how this transition happens. So part of what we're working toward is understanding more and more about this part of the universe's history. Kind of my background is in doing large cosmological simulations. So my instinct, whenever I want to learn more about something, is I say, okay, let's simulate it and visualize it. So this is a nice visualization of reionization happening. So it's a simulation conducted in a cosmological volume, a cube. So you're going to see this volume rotating, and these yellow points are galaxies. They're emitting photons, and as they emit photons, it ionizes the gas around them. So the volume is kind of rotating. I don't know, this might be a little hard to see on the screen, but the gas initially is neutral, and as it's becoming ionized, you see these pockets, these bubbles, we call them, growing around galaxies. So initially they start out small, kind of localized to just the galaxies, but eventually galaxies continue to produce photons, continue to ionize, the bubbles get larger and larger. They start to overlap a little bit. You see we're at about midway through ionization here. And something to note is that as the gas ionizes, it heats up tremendously. So it goes from just a few hundred Kelvin to over 10,000 Kelvin. And that's what you're seeing in the color here, is the temperature of the gas. And then finally, we hit this point where the whole universe is totally ionized, which, as I said, is kind of the state that we see it in today. So the goal is to try to learn more about this part of the universe's history by making connections with observations. And again, so in time, this is about 200 million years to 1 billion years after the Big Bang. In terms of cosmic redshift Z, that is starting around 25 or so, 2025, going down to about redshift 5. So that's kind of your cosmological time markers for what I'll be talking about. So one question naturally is, okay, if we don't know too much about this, how do we observe reionization? So one very promising signal is what's known as the 21 centimeter signal. So kind of at an atomic level, where this comes from is the hyperfine transition of neutral hydrogen. So you have the proton and the electron are in a spin triplet configuration. If they transition down to the spin singlet, then they emit a photon with a frequency of 1420 megahertz, or a wavelength of 21 centimeters. So that's where the name comes from. And one thing to keep in mind of what makes the 21 centimeter signal so appealing is that it gives you information as a function of redshift along the line of sight. And the reason for that is because in the rest frame, the radiation is emitted at 21 centimeters, say at redshift 10 or so. But as this photon propagates, it redshifts with the expansion of the universe, so that by the time it reaches us here on Earth, it's at a much lower frequency, say 150 megahertz or whatever it works out to exactly. So, and the idea is that if you can observe the 21 centimeter signal at different frequencies, that maps into different redshifts of observation along the line of sight. So you can turn the frequency that you observe the 21 centimeter signal at into the full tomographic history of the universe, which is really kind of cool. So you get to peek into different portions of cosmic reionization just by looking at different frequencies. So this is kind of what the 21 centimeter signal looks like at the atomic level. If you blow it up to the cosmological scale, this is a simulated volume that is 2 gigaparsec on size. So it's truly enormous. And so what you're seeing here is variations in the 21 centimeter signal near the midpoint of reionization. So the blue regions are ionized gas. So there's actually no signal there because there's no neutral hydrogen, no hyperfine transition. And then the yellow regions show signal that comes from the neutral gas. So you kind of have these pockets, this bubble structure that you see. And something to keep in mind is that it can either be seen in absorption, which we think happens at early redshifts near cosmic dawn, or an emission, which I've shown here during reionization. One catch, though, is that it is intrinsically a very faint signal. So this is kind of looking at it a different way if you were trying to observe it. The very relatively bright emission here. So this is a kind of toy example. The brightness as a function of frequency of different features. The top up here is synchrotron radiation from our own Milky Way galaxy, and at the bottom here is reionization. So you see it's intrinsically much fainter by several orders of magnitude. But one feature it does have is that it's very bumpy. It's jagged as a function of frequency. So we'll talk. So one naive thing you might try to do is take the Fourier transform and hope that it separates. So talk a little bit more about that in the next slides. But that's just kind of it's a bright signal that comes from the Milky Way, but it's very smooth. So we're kind of going to try to take advantage of that. Also want to say, of course, there are other ways to observe the high redshift universe, individual galaxies or galaxy surveys with something, say, like Roman Space Telescope, the kinetics Zimiev-Zeldovich effect, or KSZ from cosmic microwave background, Lyman alpha forest from bright quasar. So there's a lot of ways to observe reionization, and 21 centimeter is just one potential way to do that. But it certainly has the largest potential to give you a tremendous amount of information. So I'll be spending most of the talk focusing on the 21 centimeter signal. But if you have questions about other ones, I'm of course happy to chat about some of these other observational tracers. So one way we actually try to measure it in practice is by using radio telescopes. And one such instrument to do this is the Hydrogen Epoch of Reionization Array, or HERA. So this is a radio interferometer in the Karoo Desert in South Africa. and it's observing the 21 centimeter signal between about 50 and 250 megahertz. So again, because frequency converts into redshift, we're able to probe from redshift 5 to about 27. So again, we can cover the entire part of the universe's history that we're interested in. And right now, HERA is working to detect the power spectrum, kind of a statistical measurement, but in the future, it absolutely has as a goal making images similar to the ones I showed in the previous slide. So just to kind of give you a sense of scale here, so this is HERA under construction. Each of these dishes is about 14 meters across, and you see they're close packed in this kind of, if you were to have a bird's eye view, it's kind of this big hexagonal configuration. And the goal is to build 350 of these dishes to kind of completely fill the central circular area. So this is a bit of a wider shot of HERA from about 2 months ago. And so, you see the individual dishes here, and then the entire area that the footprint that HERA makes up is actually similar in size to Arecibo. May it rest in peace, unfortunately. But so that's kind of the scale that we're working with here. The Peru Desert also is home to some other radio telescopes. These white antennas you see over here are the Meerkat array. So it's really, built out in the middle of the nowhere purposely to get away from human radio interference. But I'll talk a little bit later about, unfortunately, that's still a problem. But we're working to correct it. So one last thing I'd like to talk about observationally is this concept that we affectionately refer to as the wedge. So as I talked about in the last slide, we have this very bright foreground emission from the Milky Way that's orders of magnitude brighter than the signal we're looking for, but it's very smooth. So you might hope naively that if you take a Fourier transform, all of the bright foregrounds kind of live in a confined area of Fourier space. So what I've drawn here is kind of a Fourier representation of the data, if you like. So on the x-axis here is the k-parallel mode in the plane of the sky. And then the y-axis is k-parallel, which is k-perpendicular is in the plane of the sky. K-parallel is along the line of sight on the y-axis here. So you would hope that kind of all of your foreground signal is confined to live in this purplish region kind of near the origin. And unfortunately, for reasons that are not super interesting, but are intrinsic to interferometers, it scatters that power to different portions of Fourier space. So kind of the reddish and yellowish regions have been contaminated by that very bright foreground signal, and it can, in principle, be larger than the cosmological signal that you're trying to measure. So the only part of Fourier space that is uncontaminated is whitish wedge region that we refer to. So I'll just to kind of visualize what the wedge does to your data. So I've taken the top row here is kind of the output of some simulations that I've run. So it's kind of, the truth in some sense, if you will, of what the 21 centimeter signal looks like according to the simulation. And then the bottom row, I've applied a wedge filter to that data. So what I've done is I've removed all of the Fourier modes that have been contaminated. So all that's left is just that white region of Fourier space. And you see two big things have changed. So one is I've lost an absolute reference scale. So on the top here, the purple regions are 0 and go up to the maximum value of 10 or 20 milli K or whatever it is. In the bottom, I've lost kind of that reference. I just kind of have the dynamic range. And the bigger, more striking thing is that the actual features in the map have moved. So you notice that, bright spots that are in the top row here don't necessarily correspond to bright spots in the bottom row. So if you're looking for particular features, then the wedge has kind of erased some of that information. But one thing to keep in mind is that the wedge is kind of unavoidable. So we kind of have to learn to live with it. So I'll talk a little bit about some of the ways that we kind of work around it, but just keep in mind that this is a major observational hurdle that we need to kind of get over. So, and that kind of dovetails with how do we simulate reionization? Because I've been talking a little bit about making synthetic images and comparing them with observations, and the goal is to ultimately learn about very first stars and galaxies and some of these properties of first stars that we'd like to learn. So we want to be able to make this connection between simulation or between theory and observation. And one way to do that is obviously with simulation. So what you'd like to do if you had infinite computing resources is actually run all the physics, do hydrodynamics with radiative transfer. And so that is very accurate, or as closely as we can without making our own universe with our own initial conditions and reionization properties, but it is very expensive. So this is a simulation that I've been working on now, so only a 2D slice, not fancy 3D, but hopefully you still get the picture. And it's a similar kind of story where initially portions of, we have small bubbles that form and they grow larger and larger. They start to overlap a little bit. And actually, I've paused the simulation here, not because reionization is done, obviously, but actually because I ran out of gas. So this is incredibly expensive to run. It took about 10 terabytes of memory, ran for about a week of human time, and took almost 100,000 CPU hours. So it is incredibly expensive. And furthermore, you're limited by the dynamic range that you can have in your simulations, because we think small galaxies are responsible for reionization, so that limits how big our boxes can be. So this is about 80 megaparsec on the side. And that's pretty good. Like, we want to be able to capture some of these details because the maximum resolution of something like HERA, and then even future experiments, will be able to capture some of these details. So we want to be able to get things right on these scales to compare between the observations and the models. But unfortunately, even though 80 megaparsec is relatively large, it's just a drop in the cosmic ocean of what we'd actually like to observe. So again, this is that 2 gigaparsec volume that I was showing earlier. And you see we're restricted to just a little postage stamp in the bottom left here. And this is much closer to the full field of view of the HERA instrument. And it's the scales we'd like to compare with other tracers of the high redshift universe, like the KSZ or galaxy surveys, things like that. So we'd like to be able to get things accurate on the small scales to make sure that we're appropriately testing our models, but also be able to realize very large volumes without tiling or repeating the volume that we did simulate. So one way that we can kind of meet in the middle is to use what we call semi-numeric methods. And so this is a way to kind of approximate the physics, so you don't get it totally right, but hopefully the approximations are in areas that you don't really care about, and you're still capturing the big picture kind of accurately. So 2 semi-numeric methods that I'll mention here for simulating reionization. Not going to go into details, but just kind of throw these out there. One is called 21cm fast, and another is called Z-Reion. So again, the exact details don't matter, but they're both ways of generating simulated 21 centimeter images like the one you see on the right here. So when you do these semi-numeric simulations, you might end up with something that looks like this. So this is kind of another way of thinking about reionization, is kind of reionization from the side, if you like. So on the x-axis here, we have redshift. And on the y-axis, it's the position in your volume. So the top panel here is just the ionization fraction. So on the right, we have totally neutral universe. On the left, it's totally ionized. And the middle panel here is the corresponding 21 centimeter signal. So on the left, when the universe is ionized, there's no signal. Again, no neutral hydrogen, no hyperfine transition, no 21 centimeter signal. On the right, you have fluctuations that are mostly driven by the density contrast of the underlying dark matter distribution. And down the bottom, I've computed the ionization fraction, the global fraction of gas that has been ionized as a function of redshift. And so we want to be able to quantify this ionization history. So I'll be talking a little bit about what I call Z50, which is the midpoint of reionization, and then delta Z, which is the duration. So it's kind of quantifying how this ionization history happened. So it's not the full distribution, but it gets you most of the way to understanding when and how reionization happened. And just to foreshadow a little bit, you can turn your ionization history almost one-to-one into the optical depth to reionization. So this is something that we measure with CMB experiments like Plante, for instance. And it goes into, we measure it when we measure other cosmological parameters like omega matter and H naught and things like that. So, and to note that the optical depth only depends on the average number density of electrons as a function of redshift to first order. So if you know the ionization history, then you can measure tau really well, and that in turn gives you better constraints on things like omega matter and your other cosmological parameters. So, pardon me, just to foreshadow a little bit, we're going to be interested in tau, and you get that from the ionization history. So I know that was a whirlwind introduction to the first billion years of the universe's history. So if anybody has any questions, feel free to speak up. Otherwise, I'm going to change gears a little bit and start talking about artificial neural networks. So what do I mean when I say artificial neural networks? It's just kind of simply a mathematical approximation of a biological brain. And we can talk about how good of an approximation it is. Probably not very good, but this is kind of historically the motivating context for devising these types of models in the first place. So this is some seminal work that was done by Minsky and Papert in the 1960s, where the idea is you have, in their case, they were thinking about image data. So you have an input image on the left. It passes through this network. So and again, because of the biological heritage, it has some nomenclature to go along with it. These squares are referred to as neurons, again, mimicking the neurons in the brain, and the lines connecting them are the strength of connection between neurons. So we call these weights in our network. And so you have the input image that comes in on the left. It passes through this network, through the neurons and the weights. They're well-defined mathematical operations. And at the end of the day, you have some determination D that the network has devised. And so this is kind of a general structure that can be used for a whole range of different problems you're trying to solve. So in my case, most of what I do is what we call supervised learning. And what this means is just that you give the network the input. Let's go with image data, and then you give it the answer that you want on the other side. And so what the network does is, given these constraints, you show it the input data and you tell it, okay, this is the answer you should have gotten. And then it goes through this mathematical process called backpropagation to adjust the weights in the network so that it gets a better answer next time. And that's kind of this fundamental loop that you're doing. And that's what learning is, if you like, is the network will, through these mathematical operations, update the weights so that it gets a better answer next time. So a classic example, kind of the hello world of machine learning applications, is handwritten digits. So the input data is, actually a 2D grid of pixels of, captured and digitized handwritten numbers. And then going along with that are the labels. So you can see here along the top row, it might be a little hard to see, but it's labeled 504, for instance, on the bottom. And so when you go through the process of training a network, you pass in the data and just the class or category it should have put the number into. And then that's kind of it. So that's a part of the appeal of machine learning applications is there's no intermediate summary statistic required. You can add that as extra input if you like, but it's not strictly required. And then the machine goes through the hard work of figuring out, okay, how do I tell a 2 from 7 from a 1 and so on. So it's kind of this interesting approach in that sense, in that once you've defined the network and the input data, then your job is done. Then you let the network kind of take it from there. So obviously there's lots of caveats and things to understand about what exactly is happening. But in principle, you can take just plain input data, maybe images, maybe speech, data points, whatever, and get something on the other side, which is kind of cool. And so this is a classification task here with categorizing digits. You can also do it on regression, and that's kind of more of what I'll be talking about in the next little bit. So basically, try to get a single number on the other side from your input data. So in addition to kind of this weight type of connection that I was talking about in the previous slide, you could imagine trying other mathematical operations. And one in particular that I'll be talking about because it plays a key role in my research is what we call convolutional neural networks. And all that means is that we take a convolutional layer and apply it to the input data. So this cartoon kind of visually shows what's happening with the convolution. So on the right, that yellow filter matrix is a series of values that gets passed over my input image, the green one on the left. And as it kind of slides across the input, you get different values in the pink box at the end. And so you just kind of cell by cell multiply the value in the filter matrix with the input image, and then you sum them all up, and then you get the pink box at the end. So the neat thing about convolutional layers is that it actually captures a lot of features in images. So kind of we've empirically discovered that these convolutional layers are great for analyzing input images because it captures local features in your input data. And so when you have convolutional neural networks, it's very well suited for image-based tasks. You have some other layers in there, sometimes max pooling or batch normalization. Again, the details don't matter, but it's just kind of these regularization layers that kind of help convolution layers do their job. The neat thing about convolution networks is that they may or may not include those dense networks like what I had in the previous slide. So if they, in a lot of cases they do, but if they don't, then it's called a fully convolutional network. And those networks have the nice property that they are somewhat agnostic about the scale of the input data, which is, again, a nice feature to have. So I'll talk a little bit about kind of both kinds of convolutional networks. So one last aside before we get to, big science and, important stuff is kind of just understanding what are the CNNs doing. So, like most physicists, I don't like black boxes. I try to understand what my tools are doing and how they're working. So it's important to try to understand what, I think anyway, that it's important to try to understand what these networks are actually doing. So there's a few different techniques you could take for kind of peeling back the veil and seeing what's going on with CNNs. So one is to actually visualize the filters and the intermediate layers. So when you train a convolutional network, what you're actually updating are those values in the filter. So you could take a look at what those filters look like. So this is this image on the right here in the top. It's the values of the filters of a fully trained network. And another thing you could do is imagine passing through your input data through these filters to kind of see what the intermediate ones look like. So and what features it's focusing on. So then that's what's in the bottom panel here. So the top is an input map. The filters are the output of the trained network. And then the bottom is kind of intermediate. What does that input map look like after it's gone through a few of these filtering layers? So it's kind of interesting because you can see some of the different, what essential features the network is pulling out of this particular input image. And just another way to visualize CNNs is what we call activation maximization. So this technique kind of tries to turn the problem on its head a little bit and ask, okay, what is the network actually looking for in the input data? So this is a network that I trained on reionization data, and these are different input images that kind of maximize the response of a particular neuron deep in the network. Again, details aren't super important, but the cool thing that I think is that it kind of looks like reionization. You have these pockets of bright and dark next to each other. On the right, you have structures that are kind of like bubble sizes typically. So it's kind of interesting to see what features the CNN is keying in on. So again, it's not maybe the science in its own right, but it does kind of give you an intuition to, okay, what are these networks actually doing and what kind of features in your data are they picking up on? Because this might expose something that, some correlation that you weren't expecting or some particular feature in your data that maybe you didn't realize was there. So I think it's important to keep in mind, but again, more important is the actual results. So now I'm going to talk about some specific examples of machine learning projects I've been working on. And so first, I'm going to start with inferring reionization properties from simulated data. So again, this is kind of making the connection between some of these reionization properties and are we able to recover information about reionization just from input images. So this is, so I showed this image in a previous slide, but again, the top row is kind of the output of the simulation, and the bottom row is that same input, but with the wedge filter applied. So remember, the wedge is this observational artifact that interferometers like HERA impart on data. So in order to try to, work within the wedge in some sense, I've kind of removed all of the data that would in principle be contaminated. So, and then these are the input images that I give to a convolutional neural network. So I start with just this bottom series of images. I stack them all up to make a series of images that are at different redshifts, which again correspond to different frequencies. And I treat all this whole stack as a single input image to my convolutional neural network. So it does these mathematical operations. And then on the other side, I get reionization parameters. So this is an example of a regression task where I have image data on the left, the input, and on the right, I get, two floating point numbers at the end, the midpoint and the duration of reionization. And so this is a visualization of that network architecture. On the left is my input image cube. So it's, in the X and Y are the images in the plane of the sky, and the Z axis is different redshifts, different frequencies. And then I apply these convolution operations. That's what these long skinny rectangles are doing to get progressively smaller intermediate layers. And then eventually I transition to dense layers on the right. So this is an example of a convolutional architecture that still has dense layers in it. And then the very short rectangle at the end, that kind of represents the two numbers that I get at the end of it. So again, what I do is I present the input images and labels with, okay, these are the values you should get. And the machine does the hard work of trying to be able to guess what value of Z50 and delta Z I would get for data it hasn't seen before. And that's kind of the name of the game here. So you might ask, okay, how well does it do? The answer is pretty well for simple data. And so what I've done here is, just as kind of a first step, I kept the midpoint of reionization relatively fixed, but I changed the duration. So you can, with these, again, these are with the semi-numeric reionization methods. This particular one was Z-reion. But the idea is that I want to be able to infer the reionization parameters just from the input images. And you can see I've trained the network a few different times. These are these fulls that I've labeled. And the x-axis here is the true value which you get for a parameter, and the y-axis is the predicted value. So if you're doing a really good job, it's going to lie along this the dotted line, the one-to-one line. And the top panel shows kind of the raw output, and the bottom is the fractional difference. And you see on the left for Z50, the midpoint of reionization, it does a really good job, but also you see it's a very narrow range, only from redshift 7.7 to 8 roughly, which is given our uncertainty in models about reionization, this is actually a very narrow range. In principle, you could have a much larger range for your midpoint. So this is artificially narrowed, but the duration we changed quite a bit, and you see that it does a pretty good job of recovering that. So by giving just input images, you're able to infer the duration of reionization to relatively high precision, which I think is pretty cool. You only get about 5% uncertainty. So you can say, okay, well, maybe that's a little, obviously it's a artificially simple range of input data because I've restricted the duration or the reionization history to only have certain features. So you might ask, okay, well, what if the data are more complicated? Well, one thing that kind of happens is then, well, you need a network that's more complicated to capture some of these extra features. And then when you do that, you don't want to make your network too complicated because then it's easy to fall into a trap of overfitting. So what we mean by that is that you learn your input data too well, and then you're not able to generalize to data it hasn't seen before very well. So for this project that we've been working on, we had to make the network a little more complicated, but we've also made sure that we don't make it too complicated, so it's kind of just complicated enough. And then the idea is that we want to make separate networks for data with and without this wedge filter applied, just to understand some of the differences. So here's a kind of a preview of some of the results that we're getting. So now, instead of looking at just the midpoint and duration separately, we've gone to tau. So remember, I mentioned that this tau, the optical depth to the CMB, it's a cosmological parameter we're really interested in measuring. And most of that, the value of tau is encoded in the midpoint and the duration. So we've kind of cut out the middleman here and gone right to tau. And you can see that the network does a pretty good job of recovering the value of tau for this data, which has not had this wedge filter applied. When you apply the wedge filter, the results, understandably get a little bit worse. You're working with just less information, so you can't do as good of a job inferring the full history, but it still does a very, very nice job. You are able to recover the value of tau to within about 5 or 10% accuracy, which is kind of a nice result. So, and again, this is now making the ionization history more complicated by changing the duration and the midpoint. So by changing both of these, we're covering more of the parameter space of allowed reionization histories given galaxy and star formation models. So this is a more robust network if we were to apply it to actual data. So you might say, well, again, even this is a little bit artificial, right? Because we're only looking at a semi-numeric reionization method, and we're only looking at one of them. In this case, this is Z-reion. So you might want to say, okay, what happens when you look at them both together? So this is now the two different methods side by side, 21cm fast and Z-reion. So the top panel here is showing the output of 21cm fast, and the bottom is showing Z-reion. And you see it's kind of by eye at first blush, they look pretty similar. You have similar features in both. Maybe one's a little bit smoother than the other, but in general, the features are pretty comparable between the two. So you want to, and so you might think, okay, it's relatively easy to get a network that's robust enough to do both. Unfortunately, it's not quite that straightforward. So this is showing, so before the last slide, it was just kind of visually. This is a little bit more quantitative in how similar or different they are. So these are pixel distributions as a function of redshift. So the x-axis here is the normalized value of the spin temperature, and the y-axis is for the different redshifts we're looking at. And then so it's been normalized on the dashed line, and then the solid black line shows the variance as a function of redshift. So you can see, yes, there are some differences in the pixel distribution, but again, they look pretty similar. So you might think, okay, it's straightforward to go from images of one to images of the other. And unfortunately, what we see is that is not the case. So in the left panel here, we've trained a network on just 21cm fast data and then tried to predict on Z-reion data. And then the right is the reverse. So you can see in both cases, the left much worse than the right, obviously, but you don't quite get back to the right answer when you're using the other semi-numeric method. So on the left, that's especially striking that no matter what the input value is for tau on the x-axis, you always get about the same value on the y-axis. So obviously this is not ideal because true reionization is obviously going to be much more complicated than either of these models will predict. So you might be so you're obviously worried that if you can't pass just a simple case, then you have probably no hope of doing this with real data. So what we've found is that you get much better results when you intersperse the two data products together. I mean, that's kind of intuitive, but it's a nice result that you can get this to work. So by having training and prediction data that contains output from both simulations, you're able to then get this nice result where you get accurate predictions kind of no matter what reionization history you choose. So kind of scaling this up for future applications when we'd like to compare this with actual data, it's just important to keep in mind that you want to make sure that your input space is kind of as robust and varied as possible so that you don't bias your results or you don't make bad inference based on the output of just of some of these neural network techniques. So, and I would also like to say, though, this is not unique to neural network approaches. You could do the same thing if you were looking at power spectra, for instance. It just comes into especially sharp relief when you're looking at images that kind of look the same, but clearly the network is picking up on differences that maybe the eye doesn't, and that is, but is actually present in the data. So this is kind of a window into some of the problems that you'd have to overcome when you try to do this for real on real data. So now I'd just like to switch gears a little bit, and this will be the last part I'll be talking about. These neural networks are very good at doing science, but they're also good for helping clean up telescope data to help us do better science in the future. So one thing that we have a perennial problem with is radio frequency interference, or RFI, which is a major problem in HERA data. So as I mentioned, we're observing between 50 and 250 megahertz. When you turn on your FM radio, for instance, that's right around 100 megahertz, 90 to 100 or so. So very kind of right smack in the middle of our observation window is FM radio, and then there's other sorts of terrestrial bits of interference that can affect our data. So we'd like to come up with a way that will get rid of these RFI events without throwing away too much actual data. And another motivation for this is that currently the way that HERA does RFI removal is very computationally expensive. And so kind of taking the current technique and scaling up to the full antenna or the full array when we have 350 antennas, we just can't keep up with the data volume. And the bigger problem is that it's not 100% accurate. And in particular, false negatives, by which I mean times when there was RFI that we didn't find with the RFI flagger, it affects the spectral smoothness of our average data. And to tie it all the way back to the wedge, we're relying on spectral smoothness of our data to be able to distinguish between reionization and Milky Way foreground. So if your data isn't as smooth as it should be, then you have problems that might masquerade as reionization. So it's a big systematic problem that we want to be able to combat. So one way we've looked at this, oh, and also I want to say, if some of this sounds familiar, most of this is the excellent work of Josh Kerrigan, one of Jonathan's previous students. So maybe some people are familiar with this work, but I just want to highlight it because I think it's a really excellent application of machine learning to kind of to how we're operating with the telescope. So this is kind of a few different cases of typical bits of RFI that we find in data. So you have things like the ORBCOMM communication satellites or FM radio that are very narrow in frequency. So the x-axis here is frequency and the y-axis is a function of time. So these transmitters are on a lot of the time or all the time, but they're very narrow in frequency. And so this is kind of what it looks like when we visualize our data. And also want to point out that on the left, so the data from HERA is inherently complex value, real and imaginary. So we tend to visualize it using the amplitude and the phase. So on the left is the amplitude of the data, and on the right is the phase. And you see RFI shows up both as bright spots in the amplitude and also discontinuities in the phase. So kind of these hallmarks of RFI can help you identify it. The rule of thumb I use is if human is able to distinguish these differences, then you can probably train a neural net to also find these differences. So that's kind of where we're going here. So this first type of narrowband RFI we see all the time in our data. You have intermittent transmission, which again can be localized in frequency, but maybe extends in time, but turns on and off. You have digital TV, which is still broadcasting in the frequencies we're looking at, and maybe the correlator, which is the machine that produces this data, maybe has some problems with it, so you want to be able to catch things like these. And then you have other kind of unexplained blips, so it might be on-site walkie-talkies, airplanes, aliens, who knows, whatever it is, you have some problems with your data that you want to identify and get rid of. Because again, uncaught RFI leads to problems with measured reionization down the road. So we developed an approach for doing this with machine learning. So the input is what we call visibility data. It's just the raw data from our telescope. And again, because it's complex valued, you have amplitude only or amplitude and phase were kind of two different flavors that, that were used. So what you use for your training data is you have simulated data from HERA, and then you paint the RFI on top of it. So you know exactly what it looks like and where it is. But because you don't want to specialize just to the case of simulated data, again, you kind of, similar to what we saw before, you want your input data to be as broad as the real data that you're comparing against. We also made evaluation data where we took real data from HERA and had a human identify RFI and flag it. So this is kind of building an evaluation set to compare and contrast. So, and this was a nice feature that, this was an application where we used this fully convolutional network so that it's scale agnostic, so that you can use it on kind of any size input data. So this is the network architecture that Josh came up with. So it's for those who maybe have done some machine learning in the past, it's similar to a U-net where you kind of have a series of convolutional filters to get down to a smaller data set, data size, and then transpose or inverse convolution layers to get back to the original size. And you do it both with the amplitude and phase. So if you like, it's a double U-net because you have the phase and amplitude as inputs that come back to a prediction at the end. So important question, how does it do? So this is some sample input data. On the left, again, is the amplitude of the data, and on the right is the phase. And you can see it does pretty well. So the first row here is the amplitude only CNN approach. The middle one is amplitude and phase. And then the bottom one is kind of the current RFI flagger. So maybe a little hard to see on Zoom, but there's different colors here. So orange shows RFI that was successfully identified. So good, did a good job. Red is RFI that is there that it did not find, so very bad. And then white is bits, a little bit of overflagging. So that shows where RFI, it was identified that RFI was present, even though it actually wasn't. So because RFI affects such little bits of our data, it's okay to overflag a little bit. The real problem is having a lot of red. So you can see in the bottom panel, especially, you have bits of red that the middle one doesn't. So it doesn't suffer as much from having, from letting RFI through, if you will. So this is kind of a more quantitative look at it. So the middle is, again, that amplitude and phase convolutional network approach. The bottom is the current RFI flagger. And you see, in magenta, you pay a small price of having more false positives, but importantly, in blue, you catch much more of the actual RFI. And so it's much more accurate. And then importantly, for, as I said, some of our computational expenses, it's much, much faster. And so, you know, you don't want to be too hung up on the computational performance. It's better to get the right answer, but in this case, it's kind of a a nice bonus that not only do you get a better answer, but you also get it faster. So it's definitely motivation for applying this to actual HERA data. So just wrap up quickly a little bit, talk a little bit about what I'm doing now and kind of some future projects I'm working on. One big thing is getting error bars for neural networks. So it's kind of this perennial issue where you get the answer, but you want to know, obviously, how uncertain are you? Like if I get the value of tau, what is my error bar on tau? And it's not necessarily easy to do with neural networks, but there's been a lot of research recently in using what they call approximate Bayesian neural networks, or BNNs, which kind of give you insight to what basically statistically motivated error bars. So you treat some of your points in your network as distributions rather than discrete points, and by propagating those distributions, you get nice error bars at the end. So just looking at this to give us good error bars. And then another thing that I've been looking at recently with a student is a variational autoencoder. And this is more toward the data quality side of things, but trying to get a network that is able to identify bad bits of corrupted data, potentially in new ways that we didn't imagine the data could be bad. So this is kind of trying to make it a little bit more general purpose and not rely exclusively on having very good, very varied input data. So more to come, but that's kind of what I've been thinking about recently. So just a quick summary, there's lots to learn about reionization. Machine learning can be a very useful tool for interpreting measurements that we get from instruments like HERA. And something always to keep in the back of our mind, I don't want to be all rosy and positive. We do need to understand what tools like machine learning are telling us, and really they should be used to complement existing forms of analysis rather than replace them. We want to make sure that we're still, we're understanding the science we're doing, and we're confident in the results that we get. So with that, I'd just like to say thank you very much, and I'm happy to take any questions.
Thanks, Paul. Yeah, so please, if people have questions, feel free to unmute and speak up.
I have a quick question for you, Paul.
Yeah.
Just curious with the approximate Bayesian neural networks. Do
Yeah.
you know, as far as like, I guess training time on those sorts of things, if you're treating, I'm not super familiar with machine learning, but if you're treating, I guess, nodes, for lack of better words, as a distribution instead of a single value, does that require larger training sets and or more training time to fully flesh out those distributions?
Yeah, that is actually kind of the crux of this, and what makes it a little bit hard is you're absolutely right. It does take a little more time. The bigger thing is you need much more training data, or conversely, you need smaller, less complicated networks, because, as you said, because you convert your points to distributions, and you want to be able to have that distribution be well sampled. You kind of pay this price where you need to, if you want to think of it in like an information point of view, you need to spend more of your input information on fleshing out that distribution rather than just getting the mean of it, if you like. So you're absolutely right that if you want to keep the same size network, you need more input data. I mean, you don't have to, but if you don't make it bigger, then you have a relatively broad distribution, so you don't have a very good estimate of what your errors look like. So you tend to overestimate what your errors actually are. So yeah, that is absolutely an important question, and part of what makes Bayesian networks a little bit difficult is you kind of have to rethink what you want your architecture, your network architecture to look like to get it to work.
Gotcha. Thanks.
Right, well, let me ask something, because I hadn't seen your latest result on training in 21CM fast and Z-Reion at the same time.
Okay.
Because that's something I've been really interested in for a while. We know that both Z-Reion and 21CM fast are probably wrong, and it's
Yes.
great to see that places where they're wrong in the same way, you can kind of get them not to overfit based on that. Is it going to be possible to evaluate on a radiative transfer hydrodynamic simulation, or just never going to get even one of those to this scale? I'm just trying to think how we can get the next step closer to ground truth.
Yeah, that is an excellent question, and actually something I've been thinking about too. Yeah, so as you said, we are, never is a strong word, but for the foreseeable future, we will not be able to get a radiative transfer simulation as big as one of these, even gigaparsec volume, kind of 100, 200 megaparsec. That's kind of as big as we can go. But we could make, 21CM fast or Z-Reion realizations that are that size, and that's kind of something that I've been thinking about and talking with other people about doing. Is okay, basically, you do the radiative transfer, you get one shot, but then you try to infer, the 21CM fast or Z-Reion parameters that went into it, and kind of what error bars are associated with it. So still, early days, work in progress, but yes, we definitely are thinking about it, because you're right. We know that both Z-Reion and 21CM fast are wrong. They're wrong in different ways, but they don't capture the full picture as well as radiative transfer simulations do. So it's definitely something that I'd like to do with this new radiative transfer suite I'm running, is do some machine learning with it and kind of see, okay, what can we get, what the uncertainties are in terms of these other models. It doesn't have to be machine learning, but that's kind of my approach. You could also imagine doing this in a more traditional way.
are no other questions, let's thank Paul again. I know you're all muted, so thank you for everybody. And fingers crossed the recording will come out okay, and I'll get it posted pretty soon. So thanks again, Paul.
Well, thank you very much for having me. If anybody wants to chat more, feel free to reach out by email. Always happy to chat. And thanks so much for the opportunity. This was fun.